Hey there, in this video we're going to learn about diagonalization. Harder to say than you might think. And so this has to do with a matrix. If I have a square matrix A, it's diagonalizable if I can break that matrix up into three separate matrices that are multiplied together, such that it's P times D times P inverse is what we're going to call these matrices. So if I can take a matrix A and break it down into these three, we say it's diagonalizable. Now, to find P and D, we need the eigenvalues and eigenvectors of the matrix. This is one of the things that are useful that we can get from eigenvalues and eigenvectors. So the matrix D, the one in the middle, is a diagonal matrix. So it's all zeros except for the main diagonal. And the main diagonal is made up of the eigenvalues of the matrix A. P is a matrix that's formed using the columns of the eigenvectors of A. And you do want the associated ones to match up in the rows between the D and P for all this to work out. Okay, so if a matrix is diagonalizable, I can break it down in this way. And if you're wondering why would I ever want to do this, well, it actually makes something that we haven't talked about with matrices a little bit easier, or actually a lot easier. We've never tried to take a matrix A and raise it to a power. But if I can diagonalize the matrix, it makes finding that multiplication, doing that multiplication, much, much easier. Okay, so if A is diagonalizable, we say that A and D are similar matrices. And you could also solve this equation for D so that D is equal to P inverse times A times P. Okay, and now all of this is predicated on the fact that P has an inverse. It has to have an inverse for any of this to work. If there's no inverse, it's not going to be diagonalizable. And so here's the benefit, or one of the benefits to diagonalization is the matrix A raised to the nth power is the same as taking P times D raised to the nth power times P inverse. And remember, D is a diagonal matrix, so all of its entries are zero except the main diagonal. So raising that to the nth power is really just a matter of raising the values in the main diagonal to the nth power. So much easier, particularly with high powers, to do this versus actually multiply A by itself multiple times. So that's one of the benefits of this. Okay, so when is a matrix diagonalizable? I kind of hinted at it at the previous slide there. A matrix that's an n by n matrix is diagonalizable if and only if it has n linearly independent eigenvectors. So if I have a 3 by 3 matrix, it needs 3 linearly independent eigenvectors to be diagonalizable. So this is something we can check to see if it's possible before we go about trying to find the matrices P and D and P inverse. If an eigenvector of a matrix is associated with a distinct eigenvalue, then the eigenvectors are linearly independent. So this can be a shortcut if you find the eigenvalues and eigenvectors, and each eigenvalue has a distinct eigenvector with it, or I said that backwards. Each eigenvector has a distinct eigenvalue, then you know that they are linearly independent. So it can save you some work if you notice this. So for instance, if I had a 3 by 3 matrix and I got 3 different eigenvalues, they're each going to have they're distinct from each other, and they each have a different eigenvector. So in that case, if I get 3 different eigenvalues, then I know that the eigenvectors will be linearly independent. Okay, so if an n by n matrix has n distinct eigenvalues, then it is diagonalizable. So one way to check that or prove it. Now be careful, this only goes one way. It doesn't say anything about a matrix that has a repeated eigenvalue. So let's say I had a 3 by 3 and I solved that characteristic polynomial and I got a double root, or a root with a multiplicity. It might be diagonalizable, it might not be. Right? There's no guarantee on that one. This theorem here really is only helpful to prove diagonalization if you get distinct eigenvalues. Okay, so if you're in that case where you can't use this this fact to prove diagonalization, then you can take the determinant of P. So form your eigenvectors into a matrix. That's what P is. And then you take its determinant to see if the vectors are linearly independent. Okay, and this is all facts we're pulling from our previous linear algebra units in this class. Okay, so how to diagonalize a matrix. I don't know why it says diagonalizable a matrix, but I meant diagonalize. So first step is you find the eigenvalues of the matrix, if you don't have them. And then you find the corresponding eigenvectors. And from that, you can construct P and D. So P is the matrix formed using the eigenvectors as the columns. And D is our diagonal matrix where the eigenvalues are going along the diagonal. Right? And then the last thing to check is determine if P is invertible. If it's invertible, then you know that your eigenvectors are linearly dependent, and you also know that the inverse exists. For testing purposes, I'm not going to ask you to find P inverse. I've tested you on that process of finding an inverse in the past. So here, I'm only going to ask that you actually prove that P inverse does in fact exist by taking this determinant. Okay, so let's do an example of this. Given eigenvalues and eigenvectors, right there, of A, determine whether the matrix is diagonalizable. If it is, diagonalize the matrix by finding P and D such that A equals P times D times P inverse. Okay, so I have this matrix A. It's a 2 by 2 matrix with rows 4, 1, and 2, 3. And I'm given the eigenvalues and eigenvectors. So we can kind of skip over that step, but it's the same as what we learned in the previous section. So let's say I have an eigenvalue 2 with an eigenvector 1, negative 2, and then a second eigenvalue 5 with its eigenvector 1, 1. So right off the bat, I have a 2 by 2 matrix with two distinct eigenvalues, which tells me that A is diagonalizable. So it is possible to construct P and D such that P is invertible and they multiply to give us A in this way. Okay, so that means D is going to be a diagonal matrix where zeros everywhere except the main diagonal. And I just took these in order. So my main diagonal is 2, 5, and then a 0 in the other two spots of the matrix D. And then for P, I'm going to grab my eigenvectors, and I'm going to put them in the same order. Since I use the 2 first, I'll use its eigenvector as the first column of P. And so P is gives me rows 1, 1, and negative 2, 1 from those eigenvectors. And the last thing I'm going to ask you to prove is that P is actually invertible and your eigenvectors are linearly independent. And so I'm going to take the determinant of that matrix P. So down the main diagonal, 1 times 1 minus the other diagonal, 1 times negative 2. And so let's see, that's going to be 1 plus 2 gives me 3. So I got a non-zero value for my determinant, which means that P inverse exists and my eigenvectors are linearly independent. And so I've proven that the matrix is invertible. If I needed to do something with this matrix, like raise A to a power, then I would actually go to the trouble of finding that inverse of P so that I could break A up into these 3 matrices and use that rule.